Hello everyone, welcome to this session. Can somebody please confirm whether I'm audible and my screen is visible or not?
Yes, ma'am.
Okay, okay, thank you. All right, so in this session, what we are going to do is we'll start off with practice assignment questions. I hope you would have taken a look at them and would have started answering practice as well as graded questions. So we are going to cover the practice questions, and after that we will be doing the code. We will be coding k-means from scratch. So I'll try to start from the basics, and we'll first introduce some NumPy libraries to you, which would be useful for you to be able to implement k-means from scratch. So and then we will code. So that's the plan. So let me get started with the practice assignment questions. Can you please mute yourself? There's some noise. Okay. All right. So, Samit, do you have a question? There's some noise from your side. Samit, do you have a question? Is it only my side, or are you also hearing the noise from Samit's side? Oh, yeah, it's fine now. All right. So, okay, let's get started. So you can see on my screen the first question from the practice assignment. Which of the following sequences is correct for k-means algorithm? There should actually be numbers here, 1, 2, 3, 4, 5. They are missing here. We'll get this fixed. So in k-means, what happens? The first step is to, like we discussed earlier also, in k-means, k is to be given by the user. K is a hyperparameter, right? So I hope the difference between parameters and hyperparameters is clear to everyone. Parameters are those which are found out by the model. On the other hand, hyperparameters are those parameters which have to be provided by the user before you start building any model, right? For example, if you talk about linear regression, uh, the weights w0, w1, or y is equal to mx plus c. M and c are the parameters which the model will identify for us. On the other hand, let's say if there is KNN, right? K nearest neighbor algorithm is there, and K means that we are studying here. K is something that the model does not identify. K is to be provided by the user, so it's a hyperparameter, and the best values for hyperparameters are found using hyperparameter tuning, which you would be studying later on. Okay, getting back. So k-means starts with the user specifying the value of k, which is precisely the number of clusters, right? So this should be the first step. After that, what happens? We assign that number of k number of cluster centers randomly, right? So assign cluster centers randomly, because we don't know what are the ideal centers, of course, which is what the k-means algorithm has to find out. So we start with some random values. After that, we check we're going to implement this also, so it will be good to be clear with these steps. Okay, so after we assign cluster centers randomly, this is called initialization step. After this, we check the distance of each data point from each of these means. Please note this step. We check the distance of each data point from each of these means. Let's say I consider one data point. I will check its distance from the three, let's say k is equal to 3. I'll check its distance from the three cluster centers. Whichever is the nearest, that cluster center will be assigned to this data point. Then I'll do the same for the second data point, third data point, and so on. So this way, all the data points will be assigned to some cluster, depending on which cluster center is near to them, right? So the next step here will be this, right? Assigning each data point to the nearest cluster centers. That's what we discussed. Once that is done, since this is just the initial setup and the centers were assigned randomly, obviously they have to now move. The points have to move. So once each data point has been assigned to the cluster centers, the clusters are new, right? The clusters have been newly formed now, based on which points got added to these clusters. So the next step is to compute the means of these clusters. So if 3 clusters are there, we will compute the means of each of these clusters. Okay. So recompute cluster centers or cluster means, one and same thing. So recompute cluster centers is the next step, fourth step. Once we recompute the cluster centers, once again, so we found the new means. So once again, what we will do is, for each data point, we will compute their distance from each of these means. So that step will be repeated because we have got new means now, right? So reassign each point to nearest cluster center. So these 2 steps will keep repeating. These are the initial 5 steps, and then the last 2 steps will keep repeating. Based on the number of iterations that we want to run this algorithm for. Okay, so 5, 3, 1, 4, 2 should be the correct sequence. I hope this sequence is correct, because it's clear to everyone, because we are going to follow the same sequence in a while. Okay, all right. Next question. This capital F is a function of z values. What does this represent? It represents the value of objective function. What is the objective function? Anyone? What is the objective function in k-means? Anyone would like to add? Okay, are we trying to minimize something here, or are we trying to maximize something?
Minimize.
Correct. So what are we trying to minimize here?
Minimizing the
Distance
optimized function.
Distance to the center.
from the mean.
Distance from mean. Right,
Yeah.
correct. Yeah, correct. Thanks. Please mute now. So the distance from the means for each data point is what we are trying to minimize. Now, which is the cluster assigned to a given data point that we are capturing through this Z, right? Z1, Z2, Zn will capture which cluster X1, Z1 will capture which cluster X1 is part of, Z2 will capture which cluster X2 is part of, and so on. So that's why we use this information to actually compute the value of the objective function. Now, what are we asking here? So there are several iterations. So in every iteration, these z's will change, right? That's why there is a zt here. In the next iteration, let's say t plus 1, these will be represented as zt plus 1, 1, zt plus 1, 2, and so on, zt plus 1, n. All right, so I hope this terminology is clear. Now, what are we asking? Which of the following is true? So the value of objective function in a given iteration is lesser than the next iteration, or is it equal, or is it greater? Anyone? Samit, there is some noise from your side. I know. Anyway, yeah, you would like to add? So what are we trying to do here? In every iteration, our motive is to reduce the value of objective function like we discussed. So in the next iteration, the value of objective function should be lesser than whatever it is right now, right? Lesser. So this represents the value of objective function in the iteration t1. This represents the value of objective function in iteration t. So it should be smaller, right? I hope this equation is clear to everyone. Let's move on to the next question. Mu1 and mu2 are the means of 2 clusters. Then the boundary between the 2 clusters will be, I think we discussed this in the last session. So the boundaries between the clusters in k-means, they are separate. The clusters are separated by half spaces, right? Let's say this is
perpendicular bisector.
Correct, perpendicular bisector, right? So you join these any given means, there could be k number of means, right? We are looking at k is equal to 2 here, so there are 2 means. Now how do we decide for a given data point whether it will be a part of cluster C1 or it will be a part of cluster C2? So how do we decide that? You join the 2 means, and then perpendicular bisector is what somebody also added. So you see the midpoint and then put a perpendicular line over here. So any point on the left hand side will be part of cluster mu1 and cluster C1. Any point on the right hand side will be part of cluster C2. Similarly, there could be more clusters, let's say mu3, right? So in that case also you will do the same thing. You will join these cluster the means. You will join these means, and once again perpendicular bisector is what you will find out, something like this. And these bisectors, so these are actually half spaces, they will intersect somewhere, right? Which is over here. So this is how you decide which points will be falling in which cluster. So this
hello, ma'am.
Yes.
Can you explain the half space concept a little bit?
Okay. Yeah, so should I repeat whatever I said, or anything specific you want to know?
No, ma'am, only the half space. Like it is like what it is. Like if it is suppose 4th dimension, then a 4th dimensional half space. I mean, what is this? Like,
Okay, so we are seeing in 2-dimensional first of all, but the same can be generalized for multiple dimensions as well. We are looking at a 2D case with multiple case. 2D. This is what we are looking at. This is a 2D space that we are looking at. We are assuming that there are only 2 features, right? So this is feature 1 and this is feature 2. So and there'll be points here, right? There'll be points here. All these will be points here, and we are expected to cluster them. Now the number of clusters could be anything. It could be given to us, like k is equal to 2 up to 10 or whatsoever, right? So I think you're getting confused between k and number of dimensions. So here the dimensions are 2 depending on how many features are there. So we are assuming that there are 2 features in the data, and we are assuming that so that we can visualize things. If let's say there are 3 features in the data, then there'll be one more dimension, and there'll be you need to visualize the points in the 3D space, okay, which is difficult to visualize. So we are sticking to 2D case, but the same can be generalized to higher dimension as well. Okay, so let's get back to 2D, and the k value can be any, right? Earlier there was k was 2 when we were considering only mu1 and mu2, but k can be 3, so mu3 is also there. K can be 4 also, so there'll be some mu4 as well. In that case also, what you will do is you will join each of these mu's, and then you will see the perpendicular bisectors, and wherever those bisectors meet each other, right, there'll be 4 perpendicular bisectors. Wherever they meet, that's how you will decide which space will belong to which cluster. Okay, so let's first take a look at the 3 k is equal to 3 case. So this is what we saw. Is this clear so far, whoever had asked the question?
yes, ma'am. Yes, ma'am. Actually, my question was like, which one is the half space? Like, it is one half of the space, or the
Yeah, definitely.
perpendicular
So
bisector is
yeah,
the.
yeah, it is called half space because it actually divides the space into 2 halves. So this is a 3 k is equal to 3 case, but if you look at k is equal to 2 case, let's say, let's keep things simple. So this is mu1 and this is mu2, let's say. Then this will be the bisector. So the entire 2D space, it is dividing into 2 parts. This will be the perpendicular bisector. On the left hand side, this is the half space. On the right hand side, there is another half space. Okay, it is dividing the entire space into two half spaces. That's what we mean by this. Is this clear?
Yes, ma'am, clear.
So now if let's say there is mu3 as well, k is equal to 3, there will be another perpendicular bisector, and there will be three perpendicular bisectors, right? And wherever these bisectors meet each other, that's how you will decide the area which will belong to a particular cluster. Okay, so this area you see like this. So three areas you see. I should have used different colors, but it's okay. I hope you got the point. So you should note where mu's are. I think there's a question in graded which is asking something similar. So whatever region that is formed by these half spaces, that's called Voronoi region. Okay. Now Voronoi regions are just not random regions. They should be formed by perpendicular bisectors only, right? I hope that is clear so far. So if you see some regions which are not actually formed by the perpendicular bisector, so that's not a valid division of spaces. Okay, I think there's a question in graded assignment regarding this. So you see mu's are here. Okay, and you see where this line is joining them, and then where bisector will come. So that's how the division should come. If the division is in some other angle, that should be wrong. Okay, let's say instead of this red line, I put something like this, and I say that this is a division between mu3 and mu1, that will be wrong. Why? Because it is not a perpendicular bisector. This is a perpendicular bisector. Is that clear to everyone?
Yes, ma'am, but that line, which is not the perpendicular bisector, that also creates two half spaces, right?
Yeah, but that is not a valid one. So
Yeah,
this k means
got
is
it, ma'am.
following. Yeah, k means is following a particular strategy. What is the strategy? The points, the distance from each point to the mean will be computed. Okay, so if you do like this, let's say, let's get back to what exactly you're asking. Let's say this one. So if you look at this point, let's say this point is actually nearer to mu3 than mu1, but you're putting it in c1, which is wrong, which is not how k-means works, right? Is that clear?
Yes, yes.
So it is an incorrect division. Yeah.
So, ma'am, what happens if the upper point is equidistant to two centers? It will not be changed from one section to another, one bucket to another.
So if the point is equidistant, so if you look at sklearn documentation, it assigns clusters randomly. Let's say two mu's are at the same distance from a given point, then that point will be assigned to one of these clusters randomly, something like that. So some tie breaking has to happen, and sklearn does it randomly. So we can decide on any other tie breaking strategy as well if you're actually implementing from scratch. Okay, but random works decently fine, so that's what we go with.
Okay.
All right. Okay, so where were we? Yeah, so I think this is clear to everyone. Mu1 and mu2 are muons of two clusters, and the boundary between them will be exactly at mu1 plus mu2 divided by 2 and will be perpendicular. So this should be the correct answer. Okay, next question. I've answered this question on discourse also, and I probably will show you a little demo of this also towards the end. So just stay on hold on this question, because we are going to code things, and we might probably see things in action. So let's keep it on hold. But okay, let me hear from you. These are the data points, and we run k-means on it with k is equal to 2. What do you say? What kind of clusters are we expected to see?
The second option, you told this in the previous session.
Oh, I told that. Okay.
Yes, like if the middle distance is huge, then those two lines are two different cluster, and if not, if they are close, then
Right.
the second option will be correct.
But ma'am,
Right.
in this, I think we cannot differentiate the distance between the
Distance between?
Just
Yeah.
distance between these two data sets, because
So firstly, the scales are given, the x and y axis are given, so you can get some idea. But what's your point?
my point was that as one said that it depends on the distance between these two data sets. If
These
they
two
are,
lines, right?
yeah,
Correct. That's one thing.
on that basis we have to decide which one of these will be. But in this particular question, I think, but yes, that you said that we can differentiate on the basis of the scale here given. So I got that.
No, you don't go by what I said. You think what should be happening here as per how k-means works. So I hope k-means is clear to everyone. So let's talk about it a bit. Uh, so there are two things here. These are the points in first line. Let's say these are the points in the next line. So I'm deliberately putting them quite close by. So this, let's call it D, which is very small here. Let's say 0.001, let's say. And there might be some gap between these elements as well. Right? That's another thing that we should consider. The third thing that we should consider is what is the distance, this overall distance, right? So there are a couple of parameters in play here, and we will try to understand if you apply k-means, what might happen. Now, one thing that we should note is um, the initialization of the cluster centers does play a role here, right? I think we discussed this, that it might happen that some cluster means initialization might result in local minima, while some other cluster means initialization might result in a global minima. That might happen, right? So here I want to discuss with you what might happen if 1 2 3 4 5 6 7 8 9 10 11 11, right? Good odd numbers are there. Let's say I take this as a mean, 1 2 3 4 5 6 7 8 9 10 11. This here, let's say I take these as means. Okay, now can you tell me something about what kind of clusters we might expect if we run k-means on it? Think about it.
These two,
Horizontal.
yes, horizontal. These data set are only the clusters.
So you mean this will be first cluster and this will be second cluster, like that?
Yes,
How would that happen?
because if we compute the distances, so the shortest distance will be on the same line.
Okay. Yeah.
And
So
We actually have to just join mu1 and mu2 in a line and have to half it, like perpendicular bisector. Then it will be a horizontal line.
yeah. So that's
If we
one.
place vertical line, then farthest left and right points are distance is very high.
These distances, right?
Yeah, yeah.
Yeah.
From
Right.
the vertical line, yeah, for vertical mid line.
Right. So firstly, what is in play here? The triangle law of distances, right? So if you, let's say you want to see which cluster this particular point might like to go in, right? If you look at the distance of this point from mu1 and you look at the distance of this point from mu2, which one is closer?
mu1.
Obviously
Top and
mu1,
bottom.
right?
Yeah.
Doesn't matter, even if this d is very, very small, this mu1 is always going to be closer. Now this is true for each and every point on this line. Similarly, for each and every point on this second line, mu2 will be closer. So that is going to happen when you take the initial means to be exactly in the center. On the other hand, if you take the means to be somewhere else, let's say these two, if you take the means over here, then the entire picture will change, and in that case you will get this option B, this option B kind of clusters. Okay, so it will be good to play around a little by changing these values, d values, and the distance between each point and the total number of points. So it will be a good idea to play around with them after writing the code, this is what I wanted to do after doing the code today. Anyway, so I'll show that around to you. So given this discussion, what we learn is,
Ma'am, one small question.
Yeah.
Do we have to in mu i's? Do we have to choose a particular data point from the data set, or we can choose mu from in the middle of anything? Like,
okay, so the way k-means functions is we randomly choose the initial cluster means. That's how k-means functions.
I
Well,
mean
if you
that mean okay, it should be only the data points from our data set,
hello,
or
I
it
lost you.
hello, am I audible?
Yeah, go on. I can hear you.
The mu should be our data point. Mu should be from our data point only, or it may not be our data point. Suppose 2,
Yeah, it
5,
may not be the data point.
Okay,
So
okay, yeah.
initially we choose one of the data points. Okay, the first step, the mean initialization, it is one of the data points. Okay, I'm telling you how k-means functions. Of course, if you're doing things from scratch, you can do anything, right?
Okay, initially.
Initially it is one of the data points, but as the points keep moving from one cluster to the other, when you compute their mean, they may not be the data points, of course, right? That is natural. Do you understand that?
Yes, it's clear, ma'am.
Yeah, so the means of the clusters in any intermediate iteration may not be a data point, right? So it will be somewhere in the space, okay? So that is what is going to happen. It will not be a data point in the subsequent iterations. I will show that to you.
But if we take the mu from the extreme right or left for the both the cases on the same side, how it will the clustering? No, same
Yes,
side.
same side,
Same.
okay? Yeah, again, in this case, it will be option B, this one.
No. One is on one is the upper line, another is the second the down the line below line. Okay. The
This
C1, no, left hand side.
Here, is it?
Yes.
Yeah. Even in that case, so what will happen? You start with this one, but gradually the means will shift. So after a few iterations, the means will come over here. One will come here, and the other will come here, and this will be the boundary. Okay. This will shift
I'm
gradually.
asking a question.
Yes. Yes.
Suppose some
Manu.
points are there in, say, 3 different clusters, and their means have been computed. Now we find that one of the point has a closer mean in cluster 2. But when we try to find the distance, the other points in the cluster 2 may actually be having a closer mean with, say, cluster 3. So it becomes kind of a circular equation.
No, it's not circular. That will be computed in the next iteration. See, so in a given iteration, let's say these are the means. So let's say this is one cluster, and let's say this is another cluster. So in a given iteration, these are the means. So you will find the distance. Let's say this is the point under consideration. You will compute its distance from this one and this one. This mean is nearer, so it will stay put. It is happy in its own cluster, and the same goes for this one. You will find the distance. This one is closer, so it will stay put. This one will also stay put. Let's say this point, right? Let's say it's somewhere over here. I mean, just assume that this is closer to this one. Now this will move to this cluster in the next iteration. Please note that. It's not that in the same iteration everybody will keep moving here and there. That will be chaos, right? So this point is noted that it has to move in the next iteration to this cluster. So we will note down, let's say in this iteration I5, let's say, we will note down which points have to move. So in the next iteration I6, the points which wanted to move will move, and moving will happen. Plus, what will be the other thing that will happen? The cluster means computation, recompute cluster means, right? That will happen in the next iteration. So there's no cycle here. Recompute cluster means. Is that clear?
But the mean of the first cluster will change if this particular point was huge, right? So
yeah, definitely it will change. The mean of this cluster and this cluster will change in the next iteration I6. And that is why we will check every point's distance from that new mean once again. That's what will keep happening in each iteration.
And the rest of yes, ma'am. The rest of the point will be will not be moved.
We will compute the distance of the rest of the points as well in the next iteration, because their distance might also change because the means have changed.
Yes, right? Yes, but if they are okay with their own cluster, then they will not be moved.
Obviously, yes. But we will check their distance also, because definitely, because the means are moving, the points distances might also change, right? So, yeah.
The algorithm decide which point to choose first based on the order it is sorted, or based on some computation?
No, Euclidean distance will be computed, right? No sorting.
Okay.
Yeah. All right. Okay, next, let's move on to fifth question.
Ma'am, can you hear me now?
Yes, Amit, it's clear now.
Can you just collapse that space, this importer, because then the screen is a little bit bigger. Yeah. You collapse this left-hand place.
Oh, this thing. Okay. Yeah, sure.
Yeah, thank you.
All right. Okay. Yeah, I'll increase the font if this is not good. All right, let's look at the fifth question. We are talking about the initialization step of k-means plus plus. So what happens in k-means plus plus? Anyone? How is k-means plus plus different from k-means?
We choose one point randomly, then we assign the next mu on probabilistic way.
Right. So in k-means, we've discussed that the initial means are assigned randomly. And that may not be a good assignment of initial means, because it might get stuck in a local minima. So k-means plus plus tries to handle that very issue, and it tries to make a smart initialization of cluster means. And how does it do it? It will start with one point chosen uniformly at random, which will be considered as the first cluster center. Okay, cluster center, cluster mean, one and same thing. Now it has to find k minus 1 cluster centers. So what it will do is, it will find the distance of each point from this cluster center that it has already chosen randomly. Okay. Now whichever point is farthest from this point, from this chosen cluster, that will be having highest probability of getting chosen as the next cluster mean. It is not that that point will be chosen. That point will be having the highest probability of getting chosen as the next cluster. Please note that. So let's, with this discussion, let's look at the question. The square distance, please note these are square distances. Please note that. The square distances is what is converted into the scores, as we will see. The square distances from the closest mean for 5 points are given. Which of the following is true? Any point out of these may be chosen uniformly at random as the next mean. This is incorrect, because only first point will be chosen. Now, can you tell me what will be the probability of choosing the first point out of, let's say, 100 points?
89%.
There are 100 points.
1 upon 100.
1 upon 100, right?
1 upon
Why?
100.
Because the first point will be chosen uniformly at random, which means every point will have equal probability of getting chosen as the first mean. Okay, so 100 points are there. Every point will have equal probability, which is 1 by n. Okay. Now, x3 will be chosen as its distance from the, there should be square distance here, from closest mean is largest. So 89 is the maximum. So which is for x3. So x3 will have highest probability of getting chosen, but it is not that x3 will definitely be chosen. So this is incorrect. X3 will be chosen with the highest probability, but we are not sure whether this point will definitely be chosen. So X3 has probability. So how would the probabilities be measured? Anyone?
And sum the squared distances and then take the proportion.
Yeah, we would normalize them. How? What do we mean by normalizing?
So divide by the
Divide by the sum, right? Yeah, 25 plus 67 plus 89 plus 24 plus 56, whatever that is, that will be the denominator for each of these points. And whatever we get, that is the probability for a particular point for getting chosen as the next mean.
And would the probability will be the difference of the square difference, the square difference from the means and the total, or we have to take each point and then the probability. Sorry, my question is, say 25, the mean is coming, say suppose 52 for this, and then 25 minus 52 and then square it, and then we take the sum and then take the proportion of each point, the squared points differences to the sum. Would that be better probability, or this which you're saying like 25 divided by total of this?
Shall I give an example? So and then you repeat your question if that is not clear.
Yeah, we could take this example only, like.
So here what is given, the distances are already measured and given to us, right? But I guess your doubt is about how.
Okay. This is my,
right?
Okay. I thought these are the points. Sorry.
These are not. Please note that this is
Yeah.
not the point. So let me give you an example to make it clear. So the points are given to us. Let me take a few points. These are the points. So we have to choose, let's say, 2 cluster centers initially. So K is equal to, so first cluster we will choose. There are 6 points. Every point, first point will be chosen with probability 1 by 6. Let's say we choose this. Let's say we end up choosing this point. Now we have to choose the next point for center. So what we will do is, for each point, we will compute its distance from the already chosen mean, which is 4. We square that up, okay? Let's say this is 2. 2 square is 4. This is the score for the point 3. Let's say this is also 2. Square is 4. For 0.5, let's say this is 3. 3 square is 9. The score for 0.6. Let's say this is also 3. The square is 9. Score for 0.2. Let's say this is 4. The score will be 16 for this. So these are the scores which are given to us. What we are given are square distances. Okay. These are the squared, although they're not squares, but it's okay. Okay. So these are the scores. Now we have to convert these scores into probability. 4 plus 9 plus 16 plus 9 plus 4, whatever that is. Let's say that is x, whatever. Okay. Now what you do is 4 divided by x. Every point, every score divided by x, like this. So these are now the probabilities for each of these points for getting chosen as the next cluster center. The highest probability, as we can see, is for this point 1. As you can see visually as well, this point 1 is the farthest from point 4. And what we, our motive in k-means is to have initial clusters centers as far apart as possible. So that's what is happening here. One is chosen randomly and the next will be chosen which is as far apart as possible. Not deterministically, but probabilistically. So point 1 will be chosen with probability 16 by by x, and these 2 points will be chosen with probability 9 by x. Now, can you tell me, will point 1 be always chosen certainly, or some other point like 2, 3, 6, 5 could also be chosen?
Not point, depending on your initialization.
No, which initialization?
Will be chosen.
Then always it will be 1, because that will be the far distance from the point 4.
Will be
Actually,
chosen, I think.
it may not be one because we are not using any deterministic model. We are using probabilistic model.
Probability, yeah.
Choosing one, it has the maximum probability, but not
Ma'am,
certainty.
it can be more than one if other point will have the equal distance from the
what are
core.
we talking about more than one? What is more than one?
Because ma'am, if any other point which will have the equal distance as compared to the one.
Sorry, I
Suppose-
couldn't
suppose
get what
point-
you're discussing. What is
suppose-
one here? What is one here, sir?
Next probable K-mean cluster center, cluster center.
One is a point mean.
Ma'am, which have the highest probability among all the points. Here see, one point have the highest probability 16 by x, and the other point, if other point will have the equal distance, that in that case there will be 2 points.
No, we are looking for only one point. My question was, this point one has the highest probability of getting chosen, but when you probabilistically choose points out of these 1, 2, 3, 6, and 5 with these probabilities, is it so that this point one will always be chosen as the next mean, or some other point out of 2, 3, 6, 5 could also be chosen? Yes or no?
Mathematically, this should be chosen because the algorithm will be working on some predefined formula. How would the algorithm decide that this is wrong and we have to take another point?
No wrong. So
one can be the only point because
One will be chosen.
that is the farthest from the previously chosen point. So
Yes.
Okay, tell me one thing. Tell me one thing.
I think if the probability is suppose 95%, then it is simple that out of 195 of the times cluster one will be chosen, and other 5 cases one may not be chosen and other points may be chosen.
Yeah, correct, Rakesh. Before I proceed, let me ask you a small.
Excuse me, ma'am. I got confused and unable to understand what's going on here.
All right, no problem. I'll catch you up there. Before I do that, let's say there is a biased coin. Okay. Let's say there is a unbiased coin. Simple. What is the probability of getting head and what is the probability of getting tail?
0.5.
Both are 0.5, right? So when you toss a coin, you could either get head or you could get tail, correct?
Yes.
Now let's say there's a biased coin, which means the probability of getting head, let's say, is not 0.5. Let's say P, probability of getting head is, let's say, 0.95. Okay. Now I toss this coin. What am I expected to get?
You can get either of them.
But tails also possible.
I can, so most of the times I'll get head, but I can get tail also, right? What is the probability of getting tail? 0.05. The probability of getting tail is 0.05, but I could get it, right? With this probability. There'll be so many heads, but there might be some tails as well, right? With small probability. Now, these are the points that are given, that are here, 1, 2, 3, 6, 5, and the probabilities are these. All right. These are the probabilities. Now, when you choose one, so please note, you're going to choose one point out of these with these probabilities. Obviously, there can be some other point that can be chosen as well, although with lesser probability. You could end up choosing 2 actually, and that is what you will go on with. That is the probabilistic element here. That's what I'm trying to tell you, that this is not a deterministic algorithm. If it was deterministic, if it were deterministic, we would have chosen this point only always. Now, there is a high chance that you will get one, but that is not sure. Is that clear?
How would the algorithm decide this is not to be chosen? I mean, it doesn't.
Which is not getting chosen?
I mean, the algorithm will be fixed to choose the one with the highest probability, right? It's like a how.
No.
Yeah.
So that's the concept of probability, that chance, right? The thing that has a high probability has a high chance of getting chosen, and vice versa. The thing that has
thinking as a human, but as a computer, how
no
would
computer, you can simulate this, right? If I ask you to write a code to simulate this, let's keep things simple. If I ask you to simulate this, I ask you to write a code where whenever I execute, let's say a function you create, whenever I call this function, it returns me either head or tail. Okay, so and as a parameter, let's say I give the probability of getting head. Okay, and when I call this function, I either get head or I get tail. So if I pass 0.5, I'll get almost half times head and almost half times tail, right? There can be a few here and there, but roughly that will be the behavior. On the other hand, if I pass, let's say p is equal to 0.95, then I want your function to return something like this. Can you simulate that?
Ma'am, I have a
What is the objective? If we go by the deterministic way, what would happen? Like,
yes, that's what sir the professor is covering there.
Yeah, so
it may not be guaranteed.
So when you say your weightage is assigned, so we are assigning weightage based on what we want to choose, right? Because we have so many points and we are assigning scores because we want to choose the one with the maximum probability. So isn't it the reverse, that we are assigning scores based on the distance from the point that we want to calculate it from? So the probability itself is assigned based on what we want to choose, right? So how are we leaving it to the probability?
So that is the purpose, ma'am, because otherwise the purpose will not be served for k-means. That's why we have chosen this k plus means.
Are you answering me or Advi?
I am adding the point to the...
Could you answer it, ma'am? I think
can you answer the question? Ma'am, can you answer the question?
Yeah, Advi, can you please repeat your question?
So isn't it the reverse? So we are assigning scores based on which we want to choose. For example, if we have a point that is farthest from,
right,
the closest
we want to give the highest probability to the point which is farthest, correct?
Yeah, so that is something that we are allocating, right? So it's intuitive that we want to select that, and that's why we are giving it the highest score.
Correct.
So how can we leave the system to select something that is not with the highest score?
Okay, so let's say we do not consider all this, the probabilistic approach we do not consider, and we run an algorithm, let's say another variant of k-means plus plus, which deterministically chooses the point. Let's say 16 is the highest, so it chooses 1, okay, and so on for the next cluster centers. Let's say k is equal to 4. The next 2 cluster centers also it chooses the same way. So this is a deterministic algorithm, right? But is it guaranteed that it will result into optimal clusters? Yes or no?
None of the systems have so far guaranteed optimal clusters.
Correct. Yeah, that is one thing. But here we are actually converting the algorithm to deterministic, and it is not possible to sort of guarantee that this approach is going to result into the best clusters. Let's not talk about global minima, but we cannot even guarantee that it will result into best possible clusters. So we bring in an element of probability in a hope that we might get better clusters, because it might not always be the case, because the data is actually random in real world. I mean, the data will not be, like we have seen in, these lines and all, right? The data has a lot of noise, and the kind of plot, if you see, it might be very not so clean, right? It will not be something like this, that you keep following a particular path and you reach a particular minima. So there is a randomness involved in it. So we do not want it to be a deterministic algorithm, although our hope is that we're moving in that direction by giving the highest probability to the farthest element. But there is an advantage in bringing in probability here, and I think professor also covers there that we can prove it, that we get within a particular range of the optimal global minima. I think log of something, right? Yeah. We reach in that particular range, so we can prove that. Okay. Deterministically, we may not be sure. Probably we get stuck somewhere. Probability helps us reach to places where a deterministic algorithm might not help us reach, right? Is
Okay.
that clear?
Yeah, yeah. Okay.
Okay. All right. So let's get back to the question and see. So this k-means approach should be, plus approach should be clear. I think there's a question graded as well. So that might be helpful. So X3 will be, is any question?
Yeah, about the distances, is it always square distances or it will be distances or it doesn't matter?
Yeah, these are square distances. That's what we do in k-means plus.
It's always
Yes, it's always square distances. Yes. Okay, so X3 will be chosen with the highest probability, but we're not sure whether this one will be definitely chosen. So that's the correct option. Next one, with respect to Lloyd's algorithm, partition configurations cannot repeat themselves. Yes or no?
Yes.
Yes.
Yes, they cannot.
Right, because in every iteration, it will be reducing. The objective function will be reducing, which comes from movement of points from one cluster to the other, and movement of points will happen only if the points see a closer cluster. So there are two things. The value of objective function will always reduce, and second thing is that will result in a new partition. Okay, so this they cannot repeat. This should be correct. And after doing the reassignments, you might get the same partition again. No, this is incorrect because the value of objective function has reduced and we cannot get the same partition. Hence, objective function after making the reassignment strictly reduces. Yes, we know because from how the k-means algorithm functions, we know this. Change of value of objective function indicates that the partition configuration has changed, right?
Correct.
The value of objective function will only change if the partition configuration has changed, right? For partitioning n data points across k partitions, it takes these many iterations. Is that correct or not?
Not always, ma'am. Maximum is
Not
30.
always.
Correct. This is the very upper limit actually, because it considers empty clusters and we do not allow empty clusters. So it's a much higher limit, but this higher limit actually helps us prove the convergence of the algorithm because we can never go beyond k to the n, right? So yeah, we will in practice, if you see, k-means actually gives you clusters much before k to the n. Okay. Next one, for 1000 data points, which value of k is likely to result in the maximum value of objective function? Okay, so tell me, if k is small, then you get higher objective function value, or when k is small?
K small.
It's small.
Yes.
Right, so let's say these are the points and we have only one cluster, k is equal to 1. So there will be a mean somewhere. And obviously, since there is only one mean, the distances will be much higher, and then you square them up as well. Anyway, so if on the other hand, k is equal to, let's say 2, then what happens? There'll be two means, right? If k is equal to 2, let's say these are the two clusters and these are the means. So since there are two means, the distances will reduce. Right? Hence, the value of objective function will reduce. And the extreme cases, when every point is in their own cluster, in that case, how much will be the value of objective function? Every point in their own cluster. So let's say number of points is equal to 10 and you take k is equal to 10. Every point is in their own cluster. What will be the value of objective function?
0.
0,
right? Because that point itself will be the mean. Right, and the distance from that is 0, and you sum that up, so the value of objective function will be 0. So here, if which value of k is likely to result in the maximum value, whatever is the highest. Maximum value, k is equal to 1, right?
Lowest one.
K is equal to, lowest. K is equal to 1 will result in the highest value because there's only one mean and distance will be high. Next one is also similar. 100 data points, 100k, value for objective function will be, we just now discussed, 0, right? In k-means algorithm, all cluster initializations lead to the same result.
Ma'am, when they say 100 data points and 100 clusters, we should assume that every point has its own cluster, or
Yeah, firstly, we are saying that none of the clusters will be empty, right? So you can't have an empty cluster.
So that we have to, that's a given, even
That's
without
given, yeah.
saying.
Yeah, that's given. From the way k-means functions, we know that they can't be empty clusters.
Okay.
So every point it will be in their own cluster. Okay, in k-means, all cluster initializations lead to the same result. Is that so?
No, ma'am.
The earlier question, ma'am, it means that the mean is 0 because every point is its mean. That's why it's 0.
Yes, yes, correct. Okay. So k-means all cluster initializations lead to the same result. This is incorrect.
Incorrect, yes.
One initialization might get stuck in local minima while another may lead to global minima. Yes, that is correct.
True.
One initialization may converge while another may not.
False.
Is that true?
False.
Why? Because it always converges, right?
Always converge.
Okay. The initialization of cluster centers may affect the number of iterations. Yes or no?
Yes.
Right. Okay.
It takes 2.
Yeah. All right. Outliers. What are outliers?
The ones that do not belong to a specific cluster.
Yeah, so let's say you have all the points here, and then let's say 1 or 2, 3 points are quite far away. So these are called the outliers. So if the data is such, in real world data, we do get outliers. So what might happen if that is the case? Some data sets might have outliers. So knowing the way k-means works, what do you think might happen?
It might affect the mean.
It might affect the means, right? So because what we are computing here, two things, k-means is based on means, right? How do you get the means? All the points, let's say,
it will increase the objective function also, right?
Yes, both. So 100, 200. So this is an outlier. So when you compute the mean, this is huge now, right? If it was not there, the mean was somewhere else. But the moment this one point came in, it affected the mean quite too much, right? That the mean changed its position. Earlier, if the mean was somewhere here, now the mean will come over here. Just because of the presence of these 3 points, the mean will go much farther from the non-outliers, okay? So that's one thing. And second, Euclidean distance, right? So what do? You find the square of things, right? And when the difference is much higher, let's say something like this, 1 minus 100, 2 minus 2, something like that. When you square them up, Euclidean distance increases, and this is what we use in the objective function. So objective function also changes drastically. So that's why.
How to deal with this kind of situation, ma'am?
So generally, we remove the outliers if they're much far away, right? Like this case, we might keep them aside, and we might run k-means on these data points. Okay, so it's one of the pre-processing steps in real world data that we might check the presence of outliers. So are you aware of box plots?
Yes.
Yes.
So in box plots, these are the boxes, and then there are whiskers like that, and you would have seen some dots probably like this.
Yes.
So what do these dots represent?
These are the outliers.
These are the outliers. And how do we? So given some data, how can we actually make sure that a given data point is an outlier? So how
anything is 3 sigma, beyond 3 sigma.
Yeah, if it is normally distributed, right, that's one thing, and that's correct. So there are many ways. So these points, which are outside 3 standard deviations, they are termed as outliers in case of normally distributed data. That's one way. Another way is if you know about box plot, this is your Q1, right? This point is your Q1 first quartile. This is your Q3 third quartile. This is your median, which is second quartile. And then this whisker is Q3 plus 1.5. This is IQR, interquartile range, which is Q3 minus Q1. Right? Yeah, so Q3 plus 1.5 IQR, this is your max point as per box plot. this is your min point, which is Q1 minus 1.5 IQR, right? So this is your min. If there is any other point in the data set which is out of these max and min, that is termed as outliers. So that's one rule to define outliers in data. So you might want to keep these points aside because your motive might be to get the general clustering present in the data. So you might want to do this.
But this algorithm is in itself designed to treat the outliers as a separate cluster, right? So why?
That might happen if actually they are in a cluster, okay? What if they are actually not in the form of a cluster, right?
You mean the error kind of outliers?
Yeah, these are error kind of outliers. So, but if they are in their own cluster, they're actually not outliers. Let's say like this. This is their, I won't call them outliers, right? Because they are more in number and there are they are clustered together, right? So they might not be outliers. They actually might contain some useful information about your data, right?
Right.
Is there any term called outlier cluster?
Outlier cluster, I don't know. I'll have to check. So these are outliers definitely, right? But I
if we
won't
have a
call.
cluster, it will not be an outlier, right?
Exactly, yeah.
Yes, that is my
Exactly.
point. If it is an outlier cluster, then it should be outside
Correct.
box.
I have a general question, like if a data set has like a categorical variables like a gender or a married hash, etc., and we hot code it to 10 or 01, does k means work on such kind of data? It's only all I mean kind of a numerical.
Yeah, definitely it can work. Why not? So so this 10 one hot encoded will be one of the features, right? Depending on after one hot encoding, it will get converted into some number of features, right? And that will be one of the dimensions. So we've been looking at two-dimensional case like feature 1, feature 2, but in practice will be visualize some, let's say, 1,000-dimensional data in case of 1,000 features. And those one hot encoded features will be few of them. So that will be considered, there's no issue. So what that actually means is, let's say 0 or 1 value will be there for one of the features. Let's say red, blue, and green. The color feature was encoded into these 3 columns, so something like that was the were the values after encoding. So every feature can have either 0 or 1 value. So like that we will have values, right? I'm taking 0 here, but you know that 0 will become here. But let's say this is -1. So basically you will have points over here, right? Some points here, some points here. Should be a different color. I hope you get the point. So accordingly, the points will be in different places, right?
But the mean concept won't work here, right? Because I mean, it's a sparse data kind of thing. So mean.
Yeah, data does get sparse. That is there in case of one hot encoded features. It depends on how many values are there in each categorical feature as well. But nevertheless, there are other features as well, right? It doesn't. It's not that there are only these features. There'll be some number of other features which are numerical. So combining these two kinds of features, definitely it will work the way it has been working earlier. Yeah.
Thank you.
Ma'am, what is parsed and dense data?
So you see that in this kind of data, there are so many zeros, right? One hot encoding means in each column, in each row, only one will be hot, which is 1. Okay. In this one, only again 1. In each of the rows, only one value will be 1. So most of the values will be 0. This is what we call sparse data. But if it were a numerical data, there'll be some good values here, right? In every cell, there would be some good values, and the presence of zeros will be bare minimum, right? So whatever, take some values. They are not zeros. This is dense data. This is sparse data. Okay.
Okay, got it.
All right, so getting back, I think now we can get to the coding. I don't know how many of you will be interested in doing the coding, but nevertheless, I think it will be a good idea to stay and see how we do it.
Yes, ma'am.
Yeah, give me a moment.
Ma'am, before going coding, one question can I ask?
Yeah, go.
In the question number 5, you was talking that distinguish the two data, no? The assignment question number 4.
Practice assignment?
Yes. Yeah, this one.
Yeah.
Up, the question number 4.
4.
So here the question has not mentioned, I think, distance between the two data points.
Correct. So although you can see here the scales are given, so you can see that between 1 and 5 there are how many?
Okay,
20 data points.
This is the
but,
measure scale.
No, but it should have been given. I agree with that. Also, I think I've mentioned that in discourse, but here I'll get it fixed. There should be one more option, which is depends on the initial cluster centers assignment.
Okay? Yeah, because it's distance always the partition clustering will always depend on the distance between them. No?
Distance between the data points?
No, not horizontal. The vertical distance
between the lines.
Two line, yeah.
Yeah, that's what I explained. I think I took that up sometime here.
Yeah,
so what I was telling was, if you initialize the cluster, initial cluster means mu1 and mu2 to be the midpoints of both these lines here, mu1, mu2. In that case, doesn't matter what is your D. You can try this out after we code. You can try this out. It doesn't matter if D is 1000 or D is as small as 0.001. If you take the initial cluster centers to be the midpoints of these lines, given the triangle law of distances, for any point on this line, this mu1 will be closer only than mu2. Similarly, on the second line, for any point, this mu2 will be closer than mu1. So it will stay put. This is the kind of, these are the kinds of means that will stay put even after many iterations. And hence, this will be your half space. So this will be your one cluster. This will be your another cluster. So it is depending on the initial cluster initialization. So this is a very specific case in this particular example. And any other initial means that you take, you will end up getting option B, this one. Okay.
Yeah. So I did that standard the k-mean algorithm means I use the scalar. I just designed this data set. Okay, and I use scalar and I just try to see that with all the possibility of the distance.
Okay.
So if you can check that, ma'am. So I can.
Yeah, I checked it out.
No, I'm sending the code. I sent you code.
So what is your point? After checking this, what did you get?
Yeah, so I'm thinking that at which particular point it is going to the two different thing means.
Yeah, that's what I'm telling you. If you try, you said you tried it out. So you probably would have seen if you initialize the cluster centers to be here and here, you would get this these kinds of clusters. And any other position, if you initialize the cluster means, here, anywhere else except these 2 points, you will end up getting these clusters. So I'm going to add another option here that depends on the initial cluster centers and the distance D as well. So what did you observe?
I observed I didn't assign that particular point.
Yeah, because I think sklearn assigns it randomly. I don't know how much control you get over that, right?
Yeah. So
you can get the control only if you do from
So my question was only that, so whenever we randomly do something, suppose, so in that case, up to what distance, is that any measurement that up to what distance we can get the two line as the different cluster instead of making half of the both line. So I thought that 20 data set is there. So if it's the distance between this more than 20, it will become that two different line. But
the distance between these 2 points, is it?
Yeah,
these two lines.
More than that, it's the length. Means if it is the length is here in that 4. So if the distance between this more than 4, what I saw that
yeah. What you saw?
I saw that even it is the lesser than 4 it's making. Already I have given the code. You can try on the Colab.
Okay, where is it?
In the chat box.
Okay. Yeah, we can see that. Okay, you have copied it. Yeah, we can check this out properly. So you want me to run this or what?
Yeah. So in that you're opening the Colab, no? So it's display picture and everything. So it's showing that everything. So,
okay, you want me to copy and run this? Is it?
Yeah, you can run and. Yes.
Okay. We have to actually go from side, but it's okay. We can do this also. So
ma'am,
you
there
are...
is one more point here.
Yeah. Go on.
Yeah, ma'am, in each of these lines, there are only 20 points. So there is no way you can choose the middle point
there are 20
in each of the lines.
Yeah. It has to be
an odd number of points, right?
to be able to get the exact middle
So
point.
in this particular case, even if you use k-means initialization, there is no way each one of those lines can be clustered on their own, right?
So here, did you count the points? I don't know. I didn't count it, but
Yeah,
I
there are
think
20 points.
All right. So yeah, you need the odd number of points to be able to get
Odd
the
number.
exact middle. Correct.
Yeah.
Right. So in that case, if the even number of points are there, you will end up getting the perpendicular, the vertical half space, and hence option.
Yes, ma'am.
Yeah, correct. So, did you?
Yeah. Yes. So.
What's your name? Kumar. Yes.
Yes.
So, what do you want me to do now?
Yeah. In that case, if I have taken the distance, so see that total length is equal to 20 of the each data point, and I have taken distance between these two data points is 10. And yes, and so bottom is the assignment. The label is assigning in the result bottom scalar. It is the half of the first data
This is
set.
option B, right?
Yeah, B option. It is giving the B option. But
what is the question?
If we make that more than 15, like the 17, can you go on the top?
Yeah. So you can increase the distance between these points, which you have taken to be.
Here, line P2 at the end. Can you make the 10 to 17 or 18?
This point?
Yeah, this is the distance actually.
Yeah, let's increase it much larger.
Then even if 25 is that enough, it will become completely once it is the.
Yeah, that's what. It depends on the distance between the points, and yeah, you now get the option A,
yes,
right?
Yes, that's what I was telling.
Correct.
So it was completely depend on the distance.
Not completely, because I said that because I showed you this case as well. When distance is very small, but the initializations are exact middle points, then also you will get option A. So the right way to state this.
Have we normalized it first? You have to normalize it before determining k also. No, I think the k value is showing.
Normalizing what? Sorry.
That values, that point that is showing before running for your.
So k. Okay, here in this code, he is choosing randomly because sklearn is choosing randomly. We cannot mention the particular initial k means. We cannot initialize. From scratch we can do, but here we do not have that much control. It will do randomly. Is that what you're asking?
So is it how, I mean, is this the only thing we are going to do for programming, or will we be also doing manual assignments?
Right now?
Yes, ma'am.
Yeah, definitely. He was asking this question, so I was doing this. So I'm going to do it from scratch now. How many of you are interested? Can I get a raise of hands just to get an idea of? Okay, good. All right. Very nice. Okay, so let's get started. So I don't know your background. I don't know how much NumPy you know. So definitely NumPy is going to be very useful. Can you raise your hands if you are comfortable with NumPy? All right, good. Okay. Okay, so let's get started. And NumPy we have imported. What I'll do is before we write the actual code, I will show you the usage of a few functions which we are going to use in that code, so that even if you know, it gets brushed up as to what is the usage of these functions. So how do we create an array in NumPy? Now np.array, right? Please keep responding so that I get to know that I'm not putting emphasis on something that you know already. So this is how we create an array in NumPy, and you can check the shape of the array using this attribute a.shape. This is a 1D array. Similarly, you can create a 2D array as well. You will pass a list of lists, right? So put a comma, and these are the two lists that we are passing inside the nested lists. Each of these is going to be the row in that NumPy array. Right, so these are the two rows, and then again you can see the shape using the shape attribute. Okay. Now let's go on with a few functions. I think in the code I had used numpy.random.seed. Is it clear to everyone why we have used that? So basically we are randomly generating data, right? Numpy.random.seed is used to sort of get predictable outputs from a random number generator. I'll repeat, to get predictable outputs from a random number generator. What do I mean by that? So let's see. Let's check another function and then I'll explain. Let's say if I write numpy.random.choice, what will it do? Any idea? Anyone? Let's say I pass this. What will I get? Any guesses?
Any number between 5
to 10 randomly chosen.
Any number between 5 to 10 randomly chosen, is it? I'm getting an array. So what it does is, from 0 to 5, I mean, you might need to check the documentation. From 0 to 5, it will generate 10 random numbers. This is what it does. Okay. Now, I'll run this again. I'm getting some other numbers, right? I'm getting some different numbers. So what I'll do is I'll make a small change. I'll introduce this in the beginning. So now let me run this one, and then I'll run this one. I'm getting the same numbers, right? Because I'm passing a particular seed. Now that seed will be used in generating these random numbers. So every time I run this, I will get the same numbers. This is my motive for using seed, so that you all get the same output as I am getting. Okay. All right, let's move on. So I'm just brushing up the functions because we'll be using them in a while. And this is an important function you should know about, numpy.arange. So let's say I write this. What will it give me? Any guesses? This is start. This is stop. This is step. Okay. So between 0 and 10, I'll get some numbers. 10 will be excluded, please note. And there'll be a gap of 2 in all these numbers. So that's one thing. Next is numpy.random.randn. Any guesses? Randn stands for standard normal distribution. Please note. What is a standard normal distribution? Anyone?
0, mu is 0.
Mu is 0, standard deviation is 1.
Sigma
right?
1.
Right. So that's a standard normal distribution. So from that distribution, it will generate some numbers for us that we will mention. So if I simply run it, I will get one number which follows this distribution, which has 0 mean and 1 standard deviation. I can also get multiple numbers. Let's say I pass this, which means I want a 10 cross 2 array, which is having numbers from such distribution. I'm going to use this function, so let's try to understand this. 10 cross 2, I'll be getting 10 cross 2 array I'll be getting, and each element in the array will be coming from this distribution. This distribution, mean 0 and standard deviation 1. Okay. Now let me create two functions, two arrays, small arrays, just to demonstrate something. So let's say these are my arrays, and I am going to use concatenate. It's an important function in NumPy that you should know about. So it helps us concatenate two arrays. So if, please note the double brackets because it expects a tuple as the parameter. What I am writing is numpy dot concatenate a1 comma a2. Let's see what I get. So 1, 2, 3, and then I got 4, 5, 6 in the same array. This is a useful function. This was when the arrays were 1D, right? Let's take example of 2D arrays. Let's say I have something like this, and then I have this. This is my 2D array, and then another 2D array I'll have. And then I'll do numpy dot concatenate. In the tuple, I'll pass b1 comma b2. So it's like the b1 array had two things, one thing, two thing, and then 3 and 4 also came one after the other, right? Like that. So this is how concatenation works. Okay, let's move on. So in k-means and many other ML algorithms, we are expected to find the distance between 2 points, right? Here also we have to find the distance of each point from the mean. How do we find the distance? So let's see that. So let's say a very simple array once again I'm creating. And these are the 2 points, let's say, and I want to find the distance between them. So there is a library in NumPy which is linear algebra, linalg, and it has many useful functions. One is norm that we are going to use, numpy.linearalgebra.norm. Norm is to find the norm, which is the distance, or you can say length of a given vector. So here, to find the distance between A and B, it's actually A minus B that we want to find the length of, right? So we'll pass A minus B, and that will give us the distance between A and B. So this is going to be the distance between these 2 points, A and B, points represented by these vectors. Okay. If you want to cross check, let me show that. So what exactly will be the distance between these two? If you see, if you put the Euclidean distance formula, let's cross check this. So it's square root, right? NumPy of it's square root. This is a function in NumPy. So square root of what? A1 minus B1 square. So what is A1? That is 1, and B1 is 3. So we can write 1 minus 3 square. This is square, right? Plus A2 minus B2 square. So you can write 2 minus 4 square. So this is this is the same thing, right? So I hope this is clear. Just simply writing, making use of numpy.linearalgebra.norm gives us the distance between any 2 points. You can also probably cross check this. If I pass A minus A, I'm going to get what? 0 is what I'm going to get. Right? Okay, moving on. Let's say I have
one question, Name. Is it possible to find multiple of that AB together distance from the earlier whatever you did it? like that B1 and B2 after concatenating. Let's say that it is the point P.
This point?
Yeah. So this is the one point which has the multiple points. And the next is that A and B, 2 points is there together. So is it possible we can find that
the shape should match, right? The dimension should match, right? If there is a point which is in 2D and another point is in 4D, I mean, it doesn't make sense, right? You should have the points in the same dimensions.
Okay. So we have to do individual only.
Individual of what?
Means if I want to find that so which shape we have to match with the broadcasting shape, no?
Broadcasting is not here. Broadcasting will come. Broadcasting means you're trying to add up an array with the matrix. I'll show that to you in a while. Hold that on.
Okay.
But here there's no broadcasting. But what you have to look at is the shapes of both the points between which you want to find the distance should match, right? It makes sense. That's how Euclidean distance works, right? It's a1 minus b1 square plus a2 minus b2 square plus and so on. If your vector A is 5D and your vector B is 2D, it doesn't make sense, right?
If it is the vector A is the 5 into 2 and vector B is 1 into 2, then we can.
That's not 5 into 2. That's a matrix that contains 5 points in 2D, right?
Yeah.
We will encounter such a situation where our capital X matrix will contain all the points. So what we'll do is we'll take each point one by one and we'll find the distance of each point from the mean. I'll show that to you. Okay, so yeah, another function that we're going to use. Let me first create some array. Let's say something like this. So this is our array, and if I write numpy.min of a, what am I expected to get? Anyone?
The minimum of
obviously the minimum, right? On the other hand, if I write numpy.argmin of a, what am I expected to get? What does argmin mean?
The argument that minimizes the function.
The index, right? The minimum value is -5, and what is the index of that -5 in the array? That is 6, right? Right? Is that clear?
Argument in general, is it only to find out the index, or can it be used to find the argument that gives the minimum of any function?
So you're talking about the equation where we use argmin, right?
Yes.
So actually it means the index only. So in the equation that you're talking about, let's say z, right? Let's say, I mean, if you're referring to what Sir wrote in the lectures, so that z is actually an index, right? There, that z is actually an index.
Let's take an objective function.
Objective function, right? So one thing is what is the minimum value of objective function, right? The other thing is what is the value of z that minimizes? Yeah, so correct. So there it is actually the value of the parameter, correct. So here it is the index.
Okay.
Yeah, and then that's how it is implemented in NumPy.
Okay.
Yeah. Okay, so that was argmin, and one more thing. So this is our array A. If I want to append something, if you remember lists, right, you can append things to the end of the list. You can simply write L1.append in the number. There is an append function in NumPy also, which is quite useful. The way we use it is we'll write numpy.append, after which we want to append and what we want to append. So let's say I want to append 6 at the end of A. So 6 got appended at the end. Now if I see what my A is, my A is actually same. So please note this, that it just generates a view. So if you want to actually make changes in that A itself, then you need to write A is equal to numpy.append. Okay, please note this. Now A. Now the changes have been made in A itself. So I hope that is also clear. Now this is my A. I can find the mean of the elements in A by simply writing numpy dot mean. Okay, this 2 is the mean of all these elements. This was a 1D array. Similarly, we could have a 2D array, and which is what in practice happened. So let's see how can we find the means of different axes in case of a 2D array. So if I write numpy dot mean of x, let's see what we get. Sorry, there will be a double bracket here. So it gives me the mean of all these elements, which is what I don't want. Let's say I want column wise or row wise mean. So in that case, we'll be using axis parameter, which is an important thing in NumPy. So I'll pass axis is equal to 0. And that means I want the means to be in a row, which means column wise means it will find, which means 1 plus 3 divided by 2, which is 2, and then 2 plus 4 divided by 2, which is 3. So that way I'll get the means at the bottom of my array. Okay. Next, let's take a look at broadcasting that somebody was mentioning. So this is our x, right? We have seen that. This is my x, and let's say I have an array, a vector, like let's say 1, 1, right? So if I write x plus a, what should happen? Any guesses? Any guesses what will happen here? Look at the shapes of x and a and then tell me.
It will be added row wise. Both 1 and 1 will be added to 1, 2, 3, 4.
Right. So this is called broadcasting in NumPy. The shape of x is 2 cross 2. The shape of a is 1 cross 2 basically. So this 1, 1 will be added to each row, hence making it 2, 3 and 4, 5. This is called broadcasting, and we are going to make use of it in a while. So I think these were the main functions that we are going to require to be able to code. So let's see. Let's create the data set first. It's actually there in the Colab that was supplied to you, but let me show you how the data was generated as well. It might be useful for you. So I'll first pass on a seed so that we all get the same points. These are the total number of points, let's say. And then, so what do we want here? I want 3 clusters, let's say, and I'll randomly generate the data for these. And let me make use of numpy.random.randn, which will generate data from a normal distribution with mean 0 and standard deviation 1. How many? So let's say I want 3 clusters, and I want a sort of equal number of points in each cluster. So let's say I divide n by 3, okay, and let's say because we want 2D data to be able to visualize, so I'll pass on true features. So this is what I'll pass. If you do n by 3, you might get fractional points. So it's better to do double division. It gives you floor division. Okay, so we'll get integer numbers, which is what we have to pass here in random. So this cross 2 elements will be generated. So if you want to see, let's see what we generated. This kind of data got generated. Okay, so let's say this is for first cluster, and then for second also similarly we will create, and for third also let's create. This is the kind of data we generated. This is randomly coming from the same distribution. Now let me concatenate this data because I want a capital X matrix for all the data. So I'll use numpy.concatenate. A tuple I'll pass data 1, data 2, data 3. This is my X. Let's take a look at X. Difficult to visualize like that. I mean, How do we see what kind of points got generated? So let's try to visualize that. I'll import matplotlib dot pyplot as PLT. Then how do I plot? Let's say I want to scatter plot. I need to pass x and y's here, x-axis and y-axis. So basically, the first feature should go on x-axis. The second feature should go on the y-axis. So I'll write all rows from x, all rows, and 0th column I want as the x-axis. As the y-axis, what I want is all rows and first column. Okay, this is what I want. Let me see what kind of data got generated. So this is this kind of data got generated. Is this what we wanted? Is this what we wanted? Yes or no? We wanted data in clusters, right? This is in one big cluster. This is not making any sense. So what we are, so why this is, I deliberately did this to show you this point. So all this data is coming from the same distribution, and obviously there'll be around 0, right? This, as you can see, all the points are centered around 0 and little bit scattered with the standard deviation of 1 and going up to 3 standard deviations. This is what was expected. So what we are going to, what we would have to do is we need to displace these points by some position which we will pass on. Here we'll use broadcast. So what I'll do is, for all the points that got generated here, they're randomly generated. That is fine, but I want to displace them so that I get to see some clusters. Similarly, I'll displace the points generated in the second one. Let's say whatever.
Is this because we are generating them in standard normal?
Yes, exactly. Standard normal. That's why you're getting all the points around 0, right? All the 3 data are coming.
There's a function to generate a normal distribution.
Normal. We can use that also. NumPy.random.normal. There we will be able to pass whatever mean and SD that we want. There are multiple ways to generate data, right? We can use any of these. All right, so we passed this, and then now let's see what kind of data we get. All right, so we got data in 3 clusters. Okay, now let's get started. Okay, so we need to pass the value of k. K is given to be 3 itself. So let's initialize it to 3. Now, samples we've seen, numpy.shape you can run, right? Numpy.shape, if you like write 0, that will give you the number of data points. X.shape, right? X.shape. 1998. Why this difference happened? Because floor division happened, and when it rounded off to the integer, two data point, it was less 2 data points. I hope that is clear. X.shape 1 will give you the number of features which is equal to 2, right? Okay. Now plot the data set. We have done that. Assume k is equal to 3. We have done that. Take the data points with indices these to be initial cluster centers. So actually it happens randomly, but if we do randomly, then everybody will get different results and will not be able to evaluate. So I've given these cluster centers so that we all get the same result. So 200, 800, 1200, right? 200, 800, 1200. This is a list that I'm passing. These are the cluster centers that I want. Okay. Let's see. So the points in X at these positions will be the initial cluster centers. Okay. Write a function, assign clusters. So after we initialize the points, what is the next step? We have to check each point's distance from these initial clusters to decide which cluster these points should go to, right? So assign clusters is what we have to create the function. It returns a vector z where z can be anything between 0, 1 and 2. Okay, this is just to evaluate. Okay. All right. So we need to create z, right? Let's initialize an empty array which will record the cluster indicators for each cluster. Okay. Now what we have to do? We have X, we have the cluster centers. So like I told you earlier, what we have to do is for each point in capital X, we have to see their distance, we have to compute their distance from each of the cluster centers. So definitely I have to start a loop here for each in X. What is each here? Each is a row, which is one data point. For each data point, what do I have to do? I have to find the distances from each cluster center. So let me create a list here, distance from each center, let's say. Distances from each center. Now, how do we find the distance? We have seen that numpy.linearalgebra.norm. Okay, numpy.linearalgebra.norm of what? What? The point and the cluster center. So cluster centers are here in this particular array, cluster centers. So if you write cluster centers 0, it will give you first cluster center. If you write 1, it will give you second cluster center, and so on. So we have to find the distance between each. There will be minus a minus b, right? You can write each minus cluster center I, or you can write cluster center I minus each. Anything is fine because it's a distance, it will be same. Cluster centers I minus each. I hope this is clear because we have seen the demo already. Each is a point, cluster centers I is the ith cluster. Now I, we are giving, what is I here that we need to mention. So this is list comprehension if you would have done. For I in range, what k, right? This is equal to k is equal to 3 here. So there are 3 cluster centers. There are 3 cluster centers. We'll take up one by one for each data point. So this from each center should contain the distances. Let's see. Let me
Where is K initialized?
K here.
Okay.
So print. Let's see what we get, and then it will be more clear. Let's see. So what we are getting is we are getting for each data point, we're getting its distances from each of the clusters. Now, what we have to, what was the question asking? Assign the cluster to each data point as per the distance. So let's say for one data point, these are the distances.
Now, as per the formula, we're taking distance, but in the problems we do squared distance. That does not matter, right? Because the magnitude is going to matter.
Right, correct.
Okay.
Yeah. It will be same. Yeah, because what we have to see, whichever is the minimum here, right? 5.3, let's say 1.25, 1.46. So whichever cluster has distance 1.25, this should be assigned. This should be assigned to this very data point.
And
so,
any particular reason for using squared distance in our manual calculations?
Where are we using? In k-means plus initialization, we are using square distances.
Yes. We used I mean, when we did it manually, we used square distances, right? Hello?
Can't hear you, man.
Okay.
Disconnected, I think.
Oh.
Am I audible?
Yes, ma'am. Now you're audible.
Hello. Oh, okay. Sorry, there was a power cut.
No problem.
Okay. All right. So yeah, where were we? where we are taking square distances other than k-means plus initialization?
In k-means plus initialization, we are taking square distance, and we are comparing also in the square distances. But when we are using here, we are using distance, linear algebra dot distance. Although it will not make a difference because everything is uniformly only distance. But is there any reason for us using square distance there?
In k-means plus?
Yeah. I mean, we could have used distance there only.
In k-means plus, we could have used distance also, correct? Yeah, I don't know, this is what is mentioned, but I don't, I'll have to see the reasoning why we are taking square distances.
Okay.
Yeah, I'll have to check that.
Okay.
All right. So we got these distances. Now we have to see, so this is referring to k is equal to 0, k is equal to 1, and k is equal to 2, right? So we have to see for which k the distance is small. So we can make use of argmin, right? You would have guessed that argmin can help here. So chosen cluster is equal to numpy dot argmin of what? This thing, right? Distance from each cluster. So this will give us whichever index had the smaller value for this particular data point. Let's see what kind of thing it gives us. So it gives us something like this, right? 0, 1, 2, whatever for these for each data point. But they are separate. We need to keep them together in this Z. This is what we have to return ultimately. So what we initially Z is empty. So we have to keep appending whatever we are getting. We will append it to Z. So what we can write is Z is equal to numpy dot append Z comma, what do we have to append? The chosen cluster. Okay. All right, this should be it. So let's see what ultimately is there in Z. Right. So this is what we were looking for here. The Z has to be returned and returns a vector Z where it could be 0, 1, 2. Okay. So let's convert into the form of a function now that we have seen all the components of it. So what is the name of the function? Let's take the same one. Assign clusters.
And since we are choosing random,
We can just copy
distributions. This answer will vary from user to user, right?
What is random here?
The distribution that we chose initially, the data set that we used.
We passed on the seed, right? That was the purpose of passing the seed. Okay, so everybody will get the same data, right? That was the motive.
Okay.
Is that clear?
Yeah.
Yeah. So I'm just copy pasting things here, and then what I'm doing is one moment, I'll be returning this set. Why I'm converting in function? Firstly, that's how it is asked, but we want to keep running this again and again. So so that I can show you the changes that happen across different iterations. So yeah, this should be fine. So yeah, this should be fine. Yeah. So if you want to call it, you know, you will just simply call this and it will return your this thing. Let me check if everything is fine. That is fine. All right. So this is your problem 4. Next is plot the data points with different color for different clusters. Now every data point has been assigned a cluster, which is kept in this Z cluster indicator. And any doubt? Your voice is not clear to me.
Okay, I was saying
is it only me?
No, the voice is not
me?
clear.
Not clear. Not clear.
Okay, maybe you can write in chat, Ramchandran. Okay, so this is our Z is done. Now so every point has been assigned a cluster, and let's try to visualize what kind of clusters got allocated. So again, what we can use is plt.scatter, and all rows and 0 will be your x-axis, and all rows and first column will be your y-axis. And now that we have cluster indicators for each point, so you might know that C is for color, and if you pass a list to C, every point is drawn in that color. So simply you can write C is equal to Z, and every point should have a different color. So these are kind of clusters that initially got allocated. And if you want to also show the means, right, that probably might be useful. So let me do that also. plt.scatter. What do you want? You want to display the cluster centers. Here, this contains the cluster center. So like for X, like we did for X, we can do for this also. Cluster centers, all rows and 0, and all rows and 1. And let's have a different marker, let's say plus, for showing the means. Let's have it in a larger size so that we can see it, and let's have it in a different color. It's black. What happened? Why did it go away? Let me run everything again. While it is coming, what's the next question? So now the clusters have been it's keeping on running. All right, we'll see that. So now that the clusters have been assigned to each data point, they are not good clusters, of course. So what do we have to do as a next step? We have to recompute the cluster means. Okay, compute cluster means. And how do we do that? We have to see which point falling in each cluster. Okay, after we see which points are falling in each cluster, we will take mean of that. That's what we'll do. I don't know why this is stuck. Okay, let's think about how to do the next thing. Now, how do we get the we'll look at this thing, the centroids in a while. Okay, this is fine. So you see these pluses, these are the centers, cluster centers, which were initially assigned. Now we have to recompute the cluster centers. We do that. We in each cluster, which points are falling is what we have to see. Now, before we do that, tell me what will I get if I do this? I will simply get all the points. Okay. So this basically means we are passing true for each point. Okay.
Ma'am, what is this colon comma 0 and colon comma 1? But why are we having two cluster centers in
this thing?
Yes.
This is like breaking the given data. So this is also is this clear to you? This thing?
Yes, ma'am.
Same thing.
Yeah.
Same thing. Let me explain. So this is our X. X is the data, right? Data matrix, and we have kept two features, feature 2. There are some values here and there are some values here. This is our data here so far.
I'm seeing your screen with the purity scatter still on. Maybe the screen is...
Reload the page.
Oh, is it?
Maybe like.
One
Yes.
moment. It's not streaming, is it?
It was streaming so far, but the page was stuck. Maybe you can reshare the screen again.
Yeah, I'm resharing, but streaming is happening. Yeah, I don't know. I saw start streaming somewhere, so thought it's not getting streamed, and people will say this session didn't get streamed. Anyway, so are you seeing now my notepad?
Yes, ma'am. And the video is also streaming, ma'am. Here it says streaming for us.
All right, great. Okay. So this is my X, which is my data matrix.
Still not visible.
Your page
screen is not still visible.
Notepad is not visible, is it?
Now
it's not visible, ma'am. Not visible. What's happening? I'm resharing. I'm sharing my entire screen. Okay. Do you see my notepad?
Ma'am, it loads and then it disappears, ma'am. So we're not able to...
No, nothing.
Nothing. Right now, is it visible?
Yes.
No, ma'am.
It's not visible. It's visible, right?
No, ma'am, it's not visible.
Not visible?
No, ma'am.
Oh, okay. Is my collab?
Your
voice is lagging too.
It's only black screen visible.
Yes, nothing, ma'am.
Sorry, I'm seeing broken voices. I don't know. Maybe my internet is not good.
Your internet.
Yes, ma'am. It's at your end.
Yeah, let me my internet. I think power is back or not. No, its power is not back. Looks like. Do you see my collab?
Nothing, no screen is visible.
Nothing is visible.
Just give me a moment. I'm checking my internet. Give me a moment. Internet, I don't know. I'm so sorry for this glitch, but I'll have to stick to this internet. And if the code is visible, we can quickly finish it off. It's just the last step which is remaining. Give me a moment. Is my collab visible right now?
No, ma'am, no.
If you can share the link, one of us can share the screen, ma'am.
Sorry, if I do what?
If you share your link, one of us can share the screen, ma'am, if you want.
Okay. Yeah, but who would write? Okay, I would write and...
Yeah, I can share the screen and you can continue writing.
Okay, give me a moment. It's just a 5 minutes thing which is remaining. We'll finish it off. Just give me a moment, please.
Sure, ma'am.
visible, huh?
It's visible, right?
Yeah.
It
Yeah, I
was.
got my internet back.
Yes.
Yeah. Yeah, sorry, very sorry for this delay. Okay, so yeah, Advi, so can you see my notepad?
Yes, ma'am.
Yeah, so this is feature 1, this is feature 2. How do we have to plot? So this basically the first column represents sort of x1, right? Okay, let's not use x1 because that's not how we have used in lectures. So this is feature 1, feature 2, and I want how do I plot it? This is a 2D data, and I want feature 1 on the x-axis and I want feature 2 on the y-axis, right? And this is how the data will be plotted, right? Is this clear?
Yes, ma'am.
So I want this feature 1 on the x-axis. Now, how do I extract feature 1 from this matrix X? So in NumPy, this is basically slicing that I'm doing. I want all rows. I want all rows, and I want only first column. So I'll put comma and 0. So whatever is before comma is your rows. Whatever is after comma is your columns, right? That's how we do slicing in NumPy.
So if you want first 5 rows, you'll put 5,0.
No, if you want, so 5,0 will give only 5th row and 0th column of that. If you want 5, so 0 to 5 is what you will write.
Okay.
If you okay, so colon means all rows.
Okay.
Similarly, feature 2, how would you get X and then all rows and then first column? Okay.
Got it.
Similarly, we are doing for cluster centers also when we are plotting. This is what we have done. Cluster centers, all rows 0, all rows 1. Okay. All right. So let me increase the size so that we see. Color is by default black only, so that should be fine. S. All right. Size is, I guess, increased, but it's okay. You see it, right? Color, let me change. Color is equal to black. K for black. All right. So this is what we got after the initialization. Everything else is gone, looks like. So now what we have to find the cluster means of the new clusters that we have gotten, right? So for that, we want to keep track of which elements got assigned to a particular cluster. Now I was showing you something like this. If you pass this is list comprehension that I'm passing inside X. So tell me what we will get. True for I in range, let's say x dot shape 0. Try to see what we will get here. So I'm passing this list here inside X. What will this list give me? True for I in range, x dot shape 0. X dot shape basically number of rows. So 1998, whatever that is. That many times I want true. This is what is going to be my list. Okay, I'm passing this inside X. So when you pass like this, wherever there is true, that will be printed. So everywhere there is true, so that everything will be printed. Just in case if you pass false here, everywhere there is false, so nothing gets printed. Is this clear so far? Any doubts so far?
No, ma'am.
All right. Now let me show you one more example of list comprehension where all the values are not either false or true. I hope this might also be clear to you. So false, let's say for even places I want false, for odd places I want true, something like that. So false if I mod 2 is equal to 0. Else I want true. How many times? For I in range x dot shape 0. Let's see what I get. So some places I get true, some places I get false. Now when I pass this inside my X, what is going to happen? Wherever there is true, I will get that value. Wherever there is false, I will not get that value, right? So X, let's say I pass this entire thing over here. Let's see what we get. So, okay, it's not visible like this, but let me tell you, wherever there is true, you will get the value. Wherever there is false, you will not get the value. Okay. Now, I'm explaining this because we'll be using something like this, not exactly this, but something like this. Now, what will be the output of this? Any guesses? What is Z? Z is an array that has some zeros, some ones, some twos. Now, when I write Z is equal to double equal, this is condition. So, obviously, I'll get a Boolean output. And how many Boolean outputs? Whatever the size of Z is, right? So, Z double equal 0 gives me true or false depending on wherever there is 0 in Z. Similarly, if I write Z is equal to 1, I'll get true wherever Z is 1. Similarly, if I write Z is equal to 2, I will get, you can check that out. We'll get true wherever Z is equal to, 2. Okay. Now, getting back to our algorithm, what we wanted is, we want all those values from X wherever Z is equal to 0. We want that separate. We want those values from X wherever Z is equal to 1. We want that separate, and so on. So let's put that together. So let's put that together. X, and inside that, I will pass Z is equal to I. I will represent my 0, 1, 2. How we would do that? For I in range K. K's are 3, so I will go from 0, 1, 2. Okay, so X, this will return me all those values where Z is 0, where Z is 1, where Z is 2, like that. One after the other. Okay, one after the other. This is a list. Okay. Now, once we get these values separately, we have to find their means, right? Those will be our new cluster centers. Okay. So we want those means in a list. So what I'll do is, I'm doing it step by step in the hope that everything will get clear. So the same thing I will use, because now I have to find means of those values that we have just now separated. So I'll write numpy dot mean of what? This very thing. Numpy dot mean of what? This very thing. Writing numpy dot mean of this. Okay. One more thing. How do we want means? We want means row in a row. Correct. Very good. Axis is equal to 0. Okay. Numpy dot mean of this axis is equal to 0. Now, this is where numpy dot mean gets over. This is numpy dot mean of X, Z is equal to I. This thing, axis is equal to 0. So we'll get all means in a row in the bottom. Okay. How many times do we want it? For what is I? We are using a variable, so we have to write for I in range. Okay, this is precisely what we want to do. So this should give us the means in a list. These are the 3 means, the new cluster centers that we got. Okay. What we were asking in this function, compute cluster centers, that computes the cluster centers as per Z and returns K new cluster centers. So these are our 3 new cluster centers. Now let's put everything in the form of a function. Compute cluster centers. All right. This, and inside this, what we are basically doing, we are creating new cluster centers, and how we are doing that is, these are our new cluster centers. So let me convert it into numpy dot array, because that's how we are going to iteratively do, and it will be a good idea to convert everything in the form of NumPy array so that we can apply array functions on that. So these should be our cluster centers, and this function should return those cluster centers. This should be, one moment, this should be our function. Okay. Let me call this function to make sure that everything is fine. So this function I should call, and it should return cluster centers. Let me see what I got. So this is basically our last step. Now what we have to do is just keep on repeating. So this is our function that we desire. Whatever value we're asking you to compute, you can do that, I guess. That's not a mean of the 3 clusters. Just use mean with an axis, that's all. So now let's see after the new clusters, how things have changed. So iteratively, what happens in k-means, after we got the new cluster centers, again, we will see every point's distance from these new clusters, and hence the points will be reassigned to new clusters. So let's do one thing. We'll start some number of iterations of k-means. Let's say 10 times we will run. So we have to run the 3 steps. Which steps? So one function that we had created was this assign clusters, right? I'm going to iteratively call this. Once the clusters are assigned, I want to visualize. So let me copy paste this so that we can see what is happening in each cluster. Let me write plt.show so that we can see all the clusters. Okay. So cluster centers got computed, and these cluster centers will go on over here in the next iteration. Pasted the right thing, so let's run this and see how we get to converge. So okay, so starting from here. So this was our initial thing, right? After the random initialization of means, and after this iteration happened where there are some points here, and this is our new means. I hope you can see them. And then very quickly we got the actual clusters, the inherent clustering present in the data, and rest of the iterations were actually not needed. We are running for 10 times, but you see in practice how k-means is able to actually provide us the clusters if they are like sort of well separated. If they are like entangled inside each other, then k-means will not be able to give us good results. Okay, is that clear? Any doubt in whatever we discussed? I hope now you all would be able to code it yourself, right? Okay, so that was all from my side for today's session. Still, if you have any doubts, you may please post on Discourse and I'll be answering there. Okay.
Just one question.
Yes, Samit.
The k-means algorithm, initially the first mean we chosen randomly, right? So that random selection is vary from person to person.
Yes,
suppose suppose all of us is running the k-means by selecting the first mean center as a random. Is our say after 10 step, do all 3% will land in 3 different situation or in same situation?
It depends on the initial cluster means. So it might be possible that you end up randomly choosing some cluster centers which are not good ones. For example, they all are, let's say, together. You can actually play around with this. It will be a good idea. So here I'm explicitly giving you these cluster centers so that we can evaluate your answers. But try doing randomly, or try giving, let's say, 1 to 3 as the initial cluster centers, and probably you will get stuck in local minima and you might get clusters which are not as desired, right? What do we desire? All right, close that. We want all the clusters in different, we see the clustering, inherent clustering. So if you give wrong initial centers, you might end up not getting those inherent clusters, okay?
But if we all go for the k plus plus means, then our convergence
there is a high chance that you might get, all of you or most of you might get the required clusters, okay? All right. So yeah, that was a good interaction with you all. Okay, we'll see you some other time. Please post your questions on Discourse and I'll be answering that. Thanks everyone for joining. Sorry for the glitch that happened. Okay, bye everyone.
Thanks for the session. Bye.
Thank you.